So in this video we'll prove lemmas A and B, which we stated in the previous video. So I've written up the context again here. So remember we had two chain complexes, U star, V star, W star, of which we've drawn the nth and n minus first terms here. We had chain maps I and P like this, so di is id, which means left square commutes, and dp is pd, which means right hand square commutes. And we're assuming that on each row we have a short exact sequence as part of our background assumption. And then we define the group of snakes. So a snake was a list w bar, w, v, u, u bar, which satisfies these conditions here, most of which are summarized by these kind of orange stuff here. We've got w bar as a homology class for capital W. W is a cycle that represents w bar. V is an element here in Vn, such that P of it is equal to W. And then dV has got to be equal to I of U. And U is an element, it's got to be a cycle in Zn minus 1U with I of U equals dV. And then U bar has got to be the corresponding homology class. And so lemma A said given W bar in HNW, there exists a snake W bar, W, V, U, U bar, starting with W bar. And the proof well, by definition, HNW is ZNW or BNW. So that means that we can choose W in Zn U with square bracket W as W bar. So that's our condition 2. I mean, we're given W bar in H and W, so condition 1 is satisfied, and then we can choose V as in, and then and as the rows are short exact, P is surjective. Therefore, we can choose some V in Vn with PV is going to be equal to W. So now I want to note that if we do P of dV, that's the same as d of P of V, because P is a chain map, which is d of W. But remember, W is a cycle. Okay? W is a cycle here, so dW is 0. So that's showing us that dV is in the kernel of P, which is the image of I. So I can choose some Z in UN minus 1 with I of Z. Sorry, I should call it U. I of U is D of V. Okay. And so that's almost what we said in part 4, except that we haven't checked. Here I said that U has got to be in Zn minus 1. It's got to be a cycle, so du has got to be 0. So let's check. Well, I of d of u. Okay, so that's d of I of u by because I is a chain map, which is d squared of v, because iu is dv. So substituting that here, we see that's d squared v, but d squared is 0, so that's just 0. And I is injective. Okay, right. So that's part of what it means to be a short exact sequence. The first map's got to be injective, so I is injective here. So I is injective, and I of du is u, so d of u is 0. um, uh, in other words, U is satisfies our condition 4 here. Okay. Now I can just define U bar is square bracket U to get a snake. Okay, so this process shows that we start with a homology class W bar in degree n, then we can choose a snake starting with that W bar. Okay, so now I'll prove what I'll call lemma B prime. For snake, let's call it, so it's kind of 0 W V U U bar start. We start first entry in the snake is 0. Then I want to claim that the last entry in the snake is also 0. Okay, so so look at this condition 2 here. That says that square bracket W bar is equal to square bracket W. So this says that square bracket W is 0. So what does that mean? I mean, that means square bracket W, that's another notation for the coset represented by W, W plus the Bn of capital W. So to say that the coset is 0, that means that W is in BNW. So that means that W has got to be D of W prime. Okay, so W prime is kind of up here above the end of the diagram. Okay, so okay, so now let's choose some V prime lying in Vn plus 1 with P of V prime is W prime. Okay. Okay, so okay, so P is surjective, so we can do that. Okay. So now let's so we've got this V here, and then we've got a V prime above it, and so you might ask whether dV and whether V is the same as dV prime. So let's consider at least a difference between them. So we look at the P of V minus dV prime. That's PV minus, here you've got PdV prime, but that's the same as dPV prime. Because P is a chain map. And P of V, by this condition 3 here, P of V is W. And P of V prime by P of V prime is W prime, so that's dW prime. But we said here W is equal to dW prime as we add up there, so this is just 0. So our V minus dV prime, so that's in the kernel of, this is going in the kernel of P, which is the image of I. Therefore, I can choose some U prime here in UN with I of U prime is V minus dV prime. So now let's consider I So here, now my u prime is here and my u is here. So you might ask yourself whether u is equal to du prime. So let's consider the error, the u minus du prime. We'll apply I to it. Okay, so that's so that's going to be an I of u. But I of u, remember, is dv. Well, let's write it out. So that's I of u minus, and then I've got I du prime, which is the same as d of I of u prime. Now, I of u, by what we've got here, is dv. And then, but I of u prime here is v minus dv prime, so that's dv. And then you've got a plus d squared v prime. Now, of course, the d squared is 0, so this term is 0. And dv and the dv prime, they're cancelling out. So that's equal to 0. But I is injective. So I is injective, and we've got I of u minus du prime is 0, so it follows that u has got to be equal to du prime. Okay, so this is an element now of bn minus 1u, and therefore our element u bar is square bracket u. Remember, that was our fifth condition here. But u is is a boundary. It's in the image of d, so square bracket u is 0, as claimed. Okay, so that proves our b prime. So that was lemma b prime, which is not quite the same as lemma b as we originally stated it. So that says that if w bar w v u bar and w bar, say w prime, v prime, u bar prime are two snakes starting with w bar, then the endpoints u bar and u bar prime are the same. And the proof of that is just we can just subtract Okay, so it's clear all these snake conditions we've written here, they're all compatible with the condition of subtraction. So the set of snakes is a group. So we can just subtract, that's a snake. And so now we can apply our lemma b prime to this subtracted snake. It starts with a 0 and therefore it must end with a 0. So that means that u bar is the same as u bar prime. And so now we've proved A and B, and let's just recall what we were going to do with that. We can define delta as a map from HNW to HN minus 1 U. Delta W bar is the end of any snake starting with W bar. Okay. And this and as we just mentioned already, set of snakes is a group under addition. And it follows easily from that this delta is actually a homomorphism from HNW to HN minus 1U. Okay, so now we've defined this delta, but we still need to, the whole point about defining this delta is that we're supposed to have this long exact sequence with I star, P star, and delta in it, and so we're going to need to prove exactness properties in the next video.